Hey everyone, and welcome to Net 306. Which inspection architecture is right for you? I'm Justin Davies, and I'm a Principal Solutions Architect and Network Specialist here at AWS. This session is going to focus on architecture patterns for security inspection and enforcement. And it's going to highlight one of the most popular questions we get from all kinds of customers, different industry verticals, different sizes, regardless of where they are in their cloud journey. That question is whether to centralize or distribute security inspection and enforcement. We're going to start off with a quick review on some of the new infrastructure and networking tools in the AWS toolbox that you have at your disposal for creating the security posture you desire. For example, the Route 53 resolver query logs, AWS Gateway Load Balancer, and the new AWS Network Firewall. Now, the story wouldn't be complete if we didn't touch on some of the tried and true systems, things like security groups, VPC flow logs, effective use of VPC and Transit Gateway routing tables, as well as fully managed and intelligence services, such as Amazon Guard Duty, that can take away a lot of the heavy lifting and guesswork on identifying vulnerabilities and security incidents. Now, this session is not going to focus on application-level authentication and authorization, which by no means takes a backseat to the infrastructure components that we're going to be focusing on in this 30-minute session. The second half of this session, we're going to dive into some of the implementation details on both the centralized and the distributed architecture patterns, and talk about where the AWS Network Firewall and Gateway Load Balancer can help out. We're also going to walk through some of the new functionality on the AWS Transit Gateway that simplifies some of the major pain points that folks were dealing with previously. And to set expectations correctly, we're not here to recommend one design versus the other design, but to kind of give you a framework and maybe some questions to ask your organization in order to figure out kind of the right architecture for the right reasons. When a customer asks me for advice on how to design their AWS architecture to maintain the security posture they're operating and maybe familiar with on premises, I generally start by clarifying two foundational components. That's visibility and control. Before you can control and operate any system, you need to know what that system is doing and when drifts from expected behavior occur. You need to know what expected behavior is in the first place. This is visibility. And it ranges from performance metrics such as bandwidth or CPU usage counters in CloudWatch to API transaction histories in something like CloudTrail. And sometimes it's even deeper, like inspection with tools like traffic mirroring. Control is what you do to prevent bad days. And it's generally what you do when they occur. Over the summer, we launched Route 53 resolver query logs. This was a big ask for customers who needed visibility into what resources inside their VPC were asking for. Were instances good actors and asking for DNS resolution on their application dependencies? Or were they looking up command and control servers out in the wild? Previously, customers had some pretty heavy lifting to do if they wanted this visibility. Some customers ran per instance based DNS resolution with things like DNS mask, which required configuration or an agent to run on the instance itself. Another option that customers went down the path of was launching centralized DNS servers. These were things like resolvers on EC2 instances within a VPC, again, with something like Unbound or Bind. This solved the problem of and removed the need to run an agent on all of your application instances, but it still had significant scaling issues and increased operational complexity. With the Route 53 resolver query logs, you get the full DNS request and the reply. This is also something you don't usually get with the alternative options. You get all the visibility without the issues we just addressed and can reap the benefits within a matter of minutes within your entire infrastructure. So we have DNS visibility, now we need control. It's one thing to know that your instances are asking how to get to ransomware command and control. It's another to do something actually about it. Today, customers can use Route 53 Resolver to forward unvetted queries for further inspection while not getting in the way of known or friendly queries. For example, you may want Route 53 Resolver, the default VPC resolver, to directly respond to queries for yourcompany.com and Amazon AWS.com, but send everything else over to something like the centralized instance-based solution we just touched on a second ago, to allow or deny requests at the domain level. We touched on the difference between visibility and control. There's another dimension that deserves consideration, and it applies to both visibility and control. This is where, in the path, the visibility and control is enforced. It can be out of band and passive, something like VPC flow logs, traffic mirroring, and even Amazon guard duty. Or it can be in line, in the transit path. This is where the AWS Network Firewall and Gateway Load Balancer come into play. For years, security groups have been providing a scalable, cloud-native way for customers to implement stateful, 5-tuple firewall filtering on instances within a VPC. For some customers, this wasn't enough, though, and they asked us for ways to implement deeper packet inspection. They wanted the ability to write custom rules based on payload patterns or SNI headers for HTTPS connections. This was especially important for customers with PCI-compliant workloads that needed more granular control over what entered and exited their environment. This is exactly why we launched the AWS Network Firewall. With the new AWS Network Firewall, you have a cloud-native inline layer 3 through 7 firewall solution that elastically scales with the demand of your workload and can be centrally managed. Let me repeat that last part for a second. A firewall that elastically scales and can be centrally managed. A firewall that allows you to pay for what you use, nothing more, nothing less. If you're amped about this like I am, I encourage you to check out Sec 311, which will cover the bells and whistles of the new AWS Network Firewall. For this session, again, we're going to focus on the architecture. I come across a lot of customers who have invested in a variety of comprehensive third-party security solutions and have built super strong operational practices around these offerings, both in and outside of AWS. In the past, customers struggled to provide cloud-native scalability and reliability for a lot of these third-party solutions. Customers and third-party solutions didn't necessarily have the tools available to seamlessly insert their security or other inline appliances, which made customers pick between cloud-native functionality or using their third-party firewall of choice and maybe increasing operational complexity. I couldn't be more excited that AWS has solved this problem with the launch of the Gateway Load Balancer. Gateway Load Balancer is a new type of load balancer that allows you to place appliances, aka auto-scaling fleets of instances, in the transit path, allowing you to transparently insert functionality such as deep packet inspection and enforcement without manipulating the original connection. Now, customers that used third-party firewalls before the Gateway Load Balancer were restricted by the VPC route table's requirement of a single next hop for a static route. This meant that you could only place a single third-party firewall instance in line for all of your traffic. If the instance failed, you had to get really creative to detect the failure and induce the failover to another instance. Generally, this was by API calls to update something like the relevant VPC route tables. If the instance was oversaturated with bandwidth or CPU cycles, it required even more complexity and creativity, as the VPC route table, again, only allowed a single target, and that target could not be a load balancer. Some folks took a ride on the creativity and complexity train a little further and introduced overlays like IPsec, BGP, S-NAT, and used it with the AWS Transit Gateway in order to gain the ability to load balance between multiple inline instances. You can solve any limitation with creativity, but you're typically going to have an equal or greater cost on the operational burden. With Gateway Load Balancer, it allows you to route traffic to an auto-scaling fleet of instances. It's an AWS load balancer that is now targetable in the VPC route table. Similar to other AWS load balancers, if a single instance fails, the Gateway Load Balancer can automatically remove and reroute traffic to a healthy instance. If a single instance becomes saturated, the Gateway Load Balancer dynamically scales with your auto-scaling group of appliances. This is the same foundational element that powers our AWS Network Firewall. And I believe it's a step in the right direction for empowering our third-party partner solutions to operate in the cloud as native as AWS services. If you want to deep dive into the Gateway Load Balancer, check out Net 308 for a dedicated overview. To centralize or not to centralize? That is the question. And it's also the topic we're going to dive into for the remainder of this session. For the rest of this talk, I want to focus primarily on two of the visibility and control mechanisms we touched on previously: the AWS Network Firewall and the AWS Gateway Load Balancer. In any technology system, you are typically going to be dealing with a control plane and a data plane. You can think of the control plane as the brain, the configuration, the rules. You can think of the data plane as the worker doing the work, pushing the packets and filtering the traffic. In each of the architecture patterns we will discuss, there will be both control plane and data plane components. Now, these are not mutually exclusive. And typically when folks share their desire for centralization, they typically are looking for control plane centralization and don't really care about the data plane until something like performance or cost or reliability come into play. Customers that are running inline appliance-based firewalls today typically fall into these three architecture patterns: distributed north-south, which is basically internet or outside of AWS bound; centralized north-south; and centralized east-west communication, which is basically inter-VPC inspection. The first one is the distributed north-south inspection and enforcement. This is basically inspecting traffic entering or exiting a single VPC over the internet, VPN or direct connect. Each application VPC has a firewall appliance, and it's hopefully per AZ, and it's probably running something like S-NAT. I want to point out something specific on this one, as it may not be super obvious and needs to be considered if you were thinking about deploying this model today. If you're using a firewall in conjunction with the NAT gateway, it's important to consider the placement of the NAT functionality. Today, the firewall must sit between the internet gateway and the NAT gateway due to a VPC requirement that you cannot have a more specific route in the VPC route table than the VPC CIDR itself. Now, for most use cases, this is completely fine. But if you require the visibility of the specific backend host IP, not the IP of the NAT gateway, when inspecting the traffic, then you need to deploy one of the centralized designs. Again, this typically doesn't come up, but should be considered. The second pattern is the centralized north-south. Each application VPC is connected to a transit gateway and has a default route to a centralized firewall VPC where the same type of configuration exists. Either a single firewall appliance per availability zone, performing something like S-NAT, or some of the more complex architectures with BGP and VPN overlays like we discussed a few slides ago. And that's basically to increase the number of instances per availability zone. The third pattern is centralized east-west. Each application VPC is connected to a transit gateway, but instead of routing directly to the destination VPC, it is forced through a centralized firewall VPC, where historically the same NAT functionality was required, even if it was not internet bound. This was especially relevant when the communication path involved the source and destination that may have been in a different availability zone. We're going to dive super deep into that in just a couple minutes. But before we do, let's tackle the biggest pain point that plagues all three of the patterns we just discussed. That's availability and scalability. In all three of these patterns, you'll notice that I'm forcing my traffic through a single instance via a static route in the VPC route table. If this instance fails or becomes oversaturated, you have to get super creative to detect the failure, and induce the actual failover. Usually this is done by updating the VPC route table to another instance, which, if the problem was saturation, again, it doesn't really help. In the second bucket, when I mentioned BGP and VPN overlays, it helps with some of the detection and remediation, but comes with significant complexity. And the administrative overhead, and not to mention that individual flows of throughput are limited to 1.25 gigabits per second. With the AWS Network Firewall and the Gateway Load Balancer, we no longer have this constraint. Instead of targeting a single instance, you are now targeting the cloud-native and elastically scalable AWS Network Firewall or a Gateway Load Balancer endpoint, which performs kind of all that auto-scaling and load balancing to healthy instances. Okay, now let's tackle the second biggest pain point that plagues the second and third buckets, the centralized architectures. These architectures require the use of NAT, network address translation, in order to make sure the traffic lands on the same firewall as the request. Remember, stateful firewalls require state to be effective, and asymmetric routing is one of the biggest problems stateful firewalls have to deal with. This is most prevalent in the east-west, or as we called it, the inter-VPC architecture pattern, when a client and server might be in two different availability zones. And this is a problem because of the way that the Transit Gateway's default routing algorithm works. By default, the Transit Gateway always prefers to use attachments in the same availability zone as the source of the traffic. This is on purpose, and it's to maintain AZ isolation and optimize performance. But it has its drawbacks of creating route asymmetry if you're dealing with multi-AZ communication. Okay, so let's actually spend a second to dive into this really quickly. This is where the talk probably goes from 300 to 400, so just hang with me for a second. I have two applications living in two different VPCs that need to talk with each other. I've implemented a centralized fleet of firewalls for all traffic to pass through if it leaves the application VPC. I have a transit gateway sitting in the middle to handle all of the interconnectivity and routing decisions. Each VPC has a route table entry that says, if you're looking for anything that is not local to my VPC, then go to the transit gateway. The transit gateway only has two routing tables. One that each of the application VPCs are associated to with a static route that says 0/0 or all traffic, go to my centralized firewall VPC. And a return route table that only the firewall VPC is associated to, where I have propagation turned on, to all of my application VPCs. Now, since both of the application VPCs have the same next hop requirement, the firewall VPC, I can use the same transit gateway routing table. I didn't turn on propagation on the application VPC route table because I didn't want either VPC to talk to each other directly without going to the firewall VPC first. I run my application in multiple availability zones within AWS. And in this example, application 1, where the client or source of the traffic lives, is in AZ1. This is the top left. And the server, the destination, is in AZ3, bottom left. The transit gateway, by default, follows a very specific routing algorithm. It always prefers the local AZ attachment on ingress to the transit gateway and on egress out of the transit gateway, as long as there's a corresponding attachment in the same AZ. Okay, so let's watch this play out. The packet is going to leave the source in AZ1, goes to the local transit gateway attachment in AZ1, follows the static route to the centralized firewall VPC, and uses the attachment in AZ1. The attachment is in its own subnet and route table that says 0/0, send all traffic to ENI 1, the network interface of the firewall in AZ1. Firewall does its thing and sends it back out to its ENI. That happens to be placed in another subnet with a different routing table that says, send all traffic back to the transit gateway. Takes the attachment in AZ1, the next hop is VPC2, and it was learned via the route propagation that we had turned on. And I leave the transit gateway in AZ1, across to AZ3, and to the destination. On the reply, things change. I now go to the transit gateway attachment in AZ3, and on to the centralized firewall VPC in AZ3. Now I have two choices. I could have all transit gateway attachments have a routing rule that forces all traffic, regardless of AZ, to the same firewall in a single availability zone. Or have a subnet and unique routing table per availability zone that forces traffic to the local firewall. Remember, a stateful firewall requires state. I need to make sure the traffic lands on the same firewall instance on the return path. This is no big deal if you're able to run NAT on the firewall instances, because the traffic on the return path is destined for the IP of the specific firewall instance. But again, what if you don't want to run NAT and you need to scale beyond a single instance per availability zone? That's where this model starts to fall apart. For this reason, we've created a new option on transit gateway attachments that allows you to maintain symmetric routing, ensuring that the same AZ is used for both directions of a bidirectional flow, the request and the reply, while at the same time allowing you to scale across multiple availability zones in an active-active manner, reducing your blast radius from 100% single AZ to 33% in a 3 availability zone implementation. The third and last pain point I want to talk about brings us back to the conversation around control and data plane separation. The most common reason customers and organizations deploy a centralized firewall VPC is because the teams implementing security controls are different than the teams operating the application resources. Having an account boundary between these two different functions can simplify identity and access management, but this is a control plane problem, not a data plane problem. With recent enhancements over the last few years, the ability to operate multiple accounts within a single VPC gives you the benefit of having control plane separation of duties without inducing inline data plane components, which can be expensive and add unwanted complexity. The second most common reason organizations deploy a centralized firewall VPC is to simplify the management of their security controls. By placing a few firewalls in a single VPC, it avoids the additional overhead of maintaining many distributed implementations. If this is 10 VPCs, probably no big deal. If this is 100 VPCs, it's probably a big deal. This is also a control plane issue. With the launch of the AWS Network Firewall and Gateway Load Balancer, you have the ability to get the best of both worlds, with its ability to clearly separate the control plane and data plane functionality. These systems allow you to create VPC endpoints similar to AWS Private Link that allows you to centrally manage your firewall fleet, but distribute the actual endpoints, the data plane, directly into the application VPCs and across AWS boundaries. This is where I'm going to highlight AWS Network Firewall specifically. The AWS Network Firewall has native integration with the AWS Firewall Manager, which provides a central place to configure security groups, AWS WAF, DDoS protection with AWS Shield, and stateful and stateless firewall rules with a consolidated and flexible set of common APIs. Okay, so let's recap. Gateway Load Balancer and the AWS Network Firewall now give you a cloud-native way to elastically scale your inline firewall fleet. It also provides health checks and automated remediation of failures. For VPC to VPC inspection and enforcement, we've provided a cloud-native way to maintain flow affinity on attachments that require symmetric routing, even when crossing availability zone boundaries. And both the AWS Network Firewall and Gateway Load Balancer support VPC endpoints, which allows you to simplify and centralize the administration without losing the benefits of distributing the data plane and putting your enforcement as close to the source as possible, while at the same time allowing you to maintain that separation of duties with account boundaries. So I told you at the beginning that I probably wasn't going to make any recommendations, but I'm actually going to break that. I think you want to look for opportunities to centralize control plane, but distribute the data plane components as much as you can, or your operational practices allow. If you fall into that hyperscale category, though, you're probably going to want to look at distributing some of the control plane systems as well, especially if you're dealing with extremely high frequencies of change. Another thing is that you should do the math. Most AWS services in the networking space have two cost components. There's an hourly charge to run the system and a data processing or compute volume used charge as well. If you have a ton of VPCs, but the traffic volume is small, you may want to look toward an architecture that reduces or centralizes your systems. But if you have higher bandwidth demands, you may want to push it through something like you may not want to push it through something like the Transit Gateway if you don't have to. So thanks a ton for tuning in, and I hope this session helps you think through kind of which inspection architectures are right for you.